glass has no definite crystalline structure, it's isotropic. And in fact, you'll find there are a few crystalline minerals that are isotropic as well. But the great majority of minerals are not isotropic. This is a sheet of the mineral mica. This rectangular shape we got by cutting from a larger cleavage piece. Some light very definitely gets through to your eye. The mica interacts with the polarized light to give you this splendid display of colors. Now, most minerals behave like that if you get them thin enough when you view them between two sheets of Polaroid in the cross position. Minerals like that are called anisotropic minerals. Now, watch what happens when I hold this sheet of mica parallel with the Polaroid sheet and rotate it. It goes dark 1, 2, 3, and 4 times in a complete rotation through 360 degrees. Now, those dark positions are called extinction positions, and they happen at 90-degree intervals. Now, all anisotropic minerals show that effect. All anisotropic minerals will give you 4 extinction positions, 90 degrees apart, in a full rotation when you look at them between sheets of Polaroid in the cross position. And we can explain that if we suppose that all anisotropic minerals, like this mica, can themselves polarize light into 2 mutually perpendicular directions. Let's see how that works. Light coming through the first Polaroid sheet is polarized in the east-west plane. It can't get through the second Polaroid sheet because that only lets light through that's vibrating in the north-south. Polarization directions east-west and north-south, still no light comes out of the second Polaroid sheet. The mica is in extinction. And in this position, the mica doesn't affect the passage of the polarized light. If the mica is rotated through 90 degrees, it's again in extinction because its 2 polarization directions are once again lined up with those of the Polaroid sheets. Rotated a further 90 degrees, and we see the same effect. Well, that does seem to explain some of what we see. But now let me show you that anisotropic minerals really do polarize light in 2 mutually perpendicular directions. This is a natural cleavage ROM of the mineral calcite, a special transparent variety called Iceland spar. Calcite is anisotropic. So when I put it over this dot, you see 2 images. You see 2 images because of double refraction. Now the light rays corresponding to one of those images is polarized into one plane, and the light rays corresponding to the other image are polarized in a plane at right angles to that. Now, that being the case, I can make those images disappear and reappear by rotating a sheet of Polaroid over the calcite ROM. Now let's just look at that a little bit more closely. That's the permitted direction of the Polaroid sheet. If I hold it over the calcite in that position, only one image is visible. So that image is polarized to vibrate in that plane. And if I turn that through 90 degrees, the other image appears and the first one disappears. And that means that the polarization plane of the second image must be like that. So we've got 2 directions of mutually perpendicular polarization. Now, all anisotropic minerals have that effect, but calcite's the only common mineral that shows it anything like so well. Now, there's another very important aspect of double refraction, and it's this. The light rays corresponding to those 2 images travel along different paths through the crystal, and they travel at slightly different speeds so that one set of rays lags a little bit behind the other. And that lag we call a path difference. And it's that path difference that's responsible for the interference colors that you were looking at earlier. The light that leaves the first Polaroid sheet is polarized into a single plane. When it passes through a mineral that's not in its extinction position, the light that emerges is polarized into 2 mutually perpendicular directions by the mineral. These are then polarized back into a single plane by the second Polaroid sheet. Now this light's still actually made up of the two rays that travel through the mineral at different speeds. So one ray is lagging behind the other. There's a path difference between them. If that path difference between the two waves corresponds to all wavelengths, so that the two rays reinforce each other, and you get constructive interference. But if the path difference between the two waves corresponds to an odd number of half wavelengths, then the crests of one wave will coincide with the troughs of another, and the two waves will cancel each other out. That's called destructive interference. So the effect of interference is to produce either light or darkness. The first dark band corresponds to a path difference of half a wavelength, the first light band to a path difference of a whole wavelength, and so on. And this is the effect of variable path difference when we use light of only a single wavelength. But in the microscope we use white light, and white light's a mixture of wavelengths. So instead of seeing alternating light and dark bands, you see this repeating pattern of the rainbow colors in the spectrum of white light. This progression of colors is the result of increasing path difference in anisotropic minerals. And in standard thin sections, we keep the thickness constant, so the path difference depends only on the amount of double refraction in the mineral. And in fact, in most of the minerals we're dealing with, the interference colors in standard thin sections will correspond with the lower part of this chart. But you won't see interference colors at all if you can't get rocks and minerals thin enough to see through. And up until about the middle of the 19th century, geologists had to make observations on rocks and minerals using only the naked eye or the hand lens. Till about 1850, when Henry Sorby, a scientist living in Sheffield, found through microscope slides. And this magnificent brass instrument is the very microscope that Sorby himself used. And here is one of Sorby's original thin sections. It's of a granitic rock from Aberdeen, beautifully made, and he's even engraved the locality on it and the year in which it was made, 1858.